Good morning to everybody. My name is Marco Simoncelli from Politecnico of Milano, Italy. I would like to talk about torsional behavior of fin-walled members with regular perforation systems. This work was made with Claudio Bernuzzi from Milano and Andrea Montanino from Naples. Just a very short recall on fin-walled members. Fin-walled members are steel members created by the coil-forming processes, so are different from hot-rolled members. The thickness of these members generally cannot bigger than 4.5 millimeters. With this technique, we can realize very different shapes of the profiles. Like you can see in this slide, the commonly used for the upright of the steel storage racks that are C sections, or we can also have double T sections. Generally, when we work with this profile, we can encounter in the design the problem of perforation. Is common to have perforations along the height of the members. You can see in this slide we have regular perforation system. So regular means the distance between holes is fixed along the members. You can see that we can have also different shapes of the perforation. The question is how these perforations influence the behavior of the members. It's easy to look into the new 15512 and discover the new version of 2021 and discover that there is a way to account for this perforation into the structural model, that is to create an equivalent cross-section which takes into account the perforation by reducing the thickness of the section. So you can see, for example, the thickness of this section is not constant, but we have some changes of the thickness in this point that are exactly the points in which we have perforation along the members. The problem with this procedure is that it's okay for flexural behavior. We can also estimate the primary torsional constant, so the Samvena constant, but is not adequate for the warping constant. So for the warping constant, what we can do? Now there is a research in progress in Milano in which we try to define rules for estimate the warping constant of perforated members, experimentally and numerically. Today I want just to show you theoretically and numerically approach. Very short recall on the warping constant theory. Warping constant derived from Vlasov theory and is directly connected to the sectorial area. You know, the sectorial area can be estimated by follow, let me say, the shape of the cross section. Once you know the sectorial area, it's easy to calculate the warping constant. But the very initial problem is, what is the sectorial area of a perforated cross section? We can assume on this point three different hypotheses, at least three different hypotheses. Look at this picture. Starting from picture A, which is related to the gross cross-sectional area, we have this distribution, linear distribution of sectorial area. So we can make a similar assumption when we have perforation and say, I don't care about the perforation and sectorial area remain the same. But I accounted for perforation in the calculation of warping constant. That means this part of the section will not consider in the calculation of the warping constant, but the sectoral area is not affected by this perforation. Another way, option called here C, figure C, is say the sectoral area is affected by the perforation and remain constant along the perforation length. There is another option, that is the perforation have no thickness, so the sectoral area drop to 0. You can see that these options give us very different warping constant. Starting from the gross one, we have with the option B a slight reduction of the warping constant. Option C gives us a very big reduction of the warping constant. Option D is really strange because gives us an increase of the warping constant, and this is strange. With perforation we cannot have an increase of the warping constant. To overcome this problem, we start with a mixed practical numerical procedure. So starting from the theory, from the differential equation of the torsion, so the one in which we have the contribution of the primary torsion and the contribution of the warping torsion related to the rotation. This is the second derivative and the fourth derivative. We studied a cantilever beam which is fixed in one end and with rotation or moment applied in the other end. In this example, we will have a rotation, a unit rotation in the other end. And this beam have a peculiarity to be created by different parts which are with a constant distance, perforated and unperforated part. The relationship between perforated and unperforated part is that warping constant of the perforated is equal to beta times the warping constant of the gross. So we can estimate the gross and we can say, okay, the perforated can range from 0 to 1 time the gross, so cannot be greater, so the 1 is the limit of beta, and can start from almost 0. Of course, 0 means that very big is not a real case 0, but conceptually can be also 0. We started this study with two cross sections, one called irregular and one regular. The first one is a C-section with the stiffness in the web and in the flanges. The regular one has stiffness only on the flanges. And we accounted for 3 different lengths, total length of the beam, and 3 different lengths of the perforation. That means zone A, that is the zone associated with the unperforated part, change from 120 to 240. That means 120 is the most perforated beam, because A is small and then becomes greater and the perforation is reduced. Term beta has been calibrated by the use of finite element models, very complex finite element models with a refined mesh in the thickness and in the perforation, using abacus software. From these models, I calculated the stresses and then I integrated to obtain the body moment. How it works, this procedure? The black solid line is the body moment calculated by abacus. So you can see two cases. I reported here two cases, the regular one, the irregular one, with two lengths. Here is 750, and here is 2000, the total length. So running the abacus, this is the case fixed end and unity torsion. Running the abacus, take out the stresses along all the beam, integrating the stresses to obtain the bi moment, and we obtain the black solid line. Then running the theoretical equation by changing beta from 0.7 to 1, you can see dashed lines. When dashed line and solid line are overlapped, that is the beta that we are looking for. For example, in this case, beta was 0.9, in this one was 0.8. So by using this procedure on all the section and all the length, we obtained a variability of beta, which is not depending on the total length, depends, of course, on the section shape, and depends on the perforation length, of course, but not on the total length, is not so depending on the total length. And with this procedure, we also estimate stresses in the beam. In conclusion, if we create a very big database with a very large number of cross-section and length, we can estimate a very large number of beta, so we can understand deeply how this warping, perforated warping constant is reduced from the gross one. So next step will be to use different cross-section and different length. Thank you for your attention.